Hello everyone. Welcome to part 2 of kernel trick. So in part 1, I have already described about the motivation behind kernel trick, application of kernel trick, and why taking samples to higher dimension can be really beneficial for us. So in this tutorial, we are going to talk about the math, the tricks itself, and everything else. Now there is going to be a lot of equations in this particular tutorial, but bear with me. I can assure you that after this tutorial, you are going to be able to understand pretty much everything. So there is nothing you will not understand. If you like the video, definitely make sure to subscribe. Okay, so let's start. So first of all, when I'm talking about the kernel trick, I will talk about mainly the SVM or support vector machine decision function. Now, there are many kinds of ways you can use kernel trick. You can use it with SVM. You can use it with kernel k-means. You can use it with clustering algorithms. You can use it with graph networks, etc. But if you simply understand one application, for example, is application in SVM decision function, you will understand all the other applications as well because kernel trick is used in a very similar fashion in all the other places. So bear with me. First of all, let's assume that we have n training samples. Since SVM is a supervised learning algorithm, it requires training samples, and we have n training samples, and those samples are x1, x2, x3, up to xn. So x is basically the feature of the sample, and y is the label, right? So every sample has a ground truth, output, right? Or the label, or the true output, whatever you want to call it. So those are from y1 to yn. Now, obviously, ultimately, at the end of the day, with a supervised learning algorithm or a model, you want to actually be able to predict this. So for any test sample x bar, you want to predict its ground truth, its output y bar, right? So you want to make a prediction. So what is the prediction function or decision function for SVM? So it looks something like this. There's nothing to worry about. Let me explain this. So first of all, I equal to 1 to n summation of this. This is for the n training samples. Alpha i's are nothing but parameters of SVM. You can think of it as weights, like neural networks. Neural networks has weights. Linear regression has weights. So alpha i's are also the weights of the SVM. Yi's are the y1, y2, y3, these things. Xi, you already know. These are these training samples, x1, x2, x3, up to xn. And x bar, as I told you before, it is the test sample. So in the SVM decision function, you have to take the dot product between the each training sample xi and the test sample x bar, right? And then you need to take some multiplication of the labels and the parameters of the model, and that's it. Now, this is the important part. Now, if you want to transform your sample to a higher dimension using some function phi, then what is going to happen is your decision function will look something like this, right? So xi will become phi xi and x bar will become phi x bar. That's it. It's very simple. I have done nothing complicated here. Now, in kernel trick, what we plan on doing is we plan on not making these transformations. So we plan on avoiding the phi xi and the phi x bar, but still we want to achieve this dot product. I will repeat this again. This is the most important part of today's lecture. So basically, we do not want to transform xi to a higher dimension using phi. We do not want to transform x bar to a higher dimension using phi. But what we do want is we want to replace this dot product with something which is the same as applying these transformations and then doing the dot product. So now I will give you an example. I will give you an example of a kernel, which is known as polynomial kernel. Just to be a little bit more like frank, I want to say that it's two-dimensional or 2D polynomial kernel because there is a whole square term, which I will show you now. So I'm going to show how this kernel implicitly or indirectly take the one-dimensional feature to three-dimension. So first of all, let us assume that we have two samples, xi and x bar. So xi is one feature of the sample xi. So we are assuming that it's 1D feature. And then we have x bar, which is one feature of the sample x bar. What phi does is it actually performs this transformation. So it makes xi into xi square, half, and it turns x bar into x bar square, half. Okay. So now, as you know from the previous slide, that we need to do phi xi into phi x bar. If you don't remember, let me go again. You need to do phi xi into phi x bar, right? So let us do that. So if we do that, then this is what we are doing here. If we break this down even further, then this is what happens, right? If we multiply these two things, then ultimately this is what we get. And this is equal to phi xi into phi x bar. I think this is very clear to everyone. Now understand that this term right here does not require any transformation of xi and x bar to this 3-dimension, right? We can simply take xi, which is 1D. We can simply take x bar, which is also 1D. We can multiply them together and add half and do a whole square, which is a very simple operation. This operation is actually equivalent to first transforming xi to 3D, then transforming x bar to 3D, and then doing the dot product. That means what we can simply do is we can simply replace this whole term that you can see in the brackets by this xi x bar plus half whole square. And that will actually make the model think that we have actually in reality transformed xi to 3D and transformed x bar to 3D when we actually didn't do any of these. This is basically called kernel trick. That's it. There is nothing more complicated. There is nothing complicated here. This is as complicated as it is. Let me give you another example just to be clear. Let me now give you an example of a polynomial kernel which takes a 3D feature sample to 9-dimensional. So suppose we have these two samples here, x bar and y bar. So x bar has x1, x2, x3, these three features, and y bar has y1, y2, y3, these three features. And we have defined this transformation function phi, which takes each of these samples to 9 dimensions. So you can read in these dimensions. These are x1 square, x2 square, x3 square, x1, x2, x3, x3, and so on and so forth. And y is similar, as you can understand, it will be y1, y2, y3. So it is going to be y1 square, y2 square, y3 square, y1, y2, y2, y3, and so on and so forth. So you get the idea, right? So these are the two transformations. Now we obviously need to do the dot product, right? So let's do the dot product. So if we do the dot product of these two things, this phi x and this phi y bar, you can do the math. You are going to get this formula, x1 y1 plus x2 y2 plus x3 y3 whole square, which can be shortened by x bar dot y bar whole square. Again, pause for a moment, think about it. X bar is nothing but this 3D feature, this 3D sample. Y bar is nothing but this 3D sample. We are simply doing a dot product and doing a whole square. Doing this is equivalent to transforming x bar to 9D, which is phi x bar, transforming y bar to 9D, which is phi y bar, and then taking the dot product. So understand that if we simply replace, let me again go here, phi x and phi xi and phi x bar by this formula. I mean, here this will be x bar and this will be xi bar in the formula that I was showing previously. If we simply replace it with this formula, it is the same as doing this big transformation, right? So this is the kernel trick. So the model doesn't really understand that this transformation didn't actually happen in reality. The model thinks in his mind that probably the sample is 90 because that is how the dot product looks like. Is it clear? I will now show you one final thing, which is a very famous kernel for support vector machines and all the other algorithms, whether you work with kernel k-means or any other thing, which is known as the RBF kernel. The full name is radial basis kernel function. I will repeat, radial basis function, function kernel, whatever. Now, radial basis function takes your sample towards infinite dimension. theoretically. How? I will now explain this in detail, and I can guarantee you that after this explanation, you are going to be able to understand this in a fully. Basically, there will be no confusion. So let's start. First of all, let's say we have two samples, X and Y, and just for simplicity, let's think that these are one-dimensional sample, right? Just one value. So sample X has one feature X, and sample Y has one feature Y. That's it. And this transformation phi makes this transformation. So it transforms X into X, comma X square, comma X cube, comma X to the power 4, X to the power 5, up until X to the power infinity. And similarly for Y. Now, if we apply phi X dot phi Y, I am going to now show you that it is actually equivalent to something like this, which is basically e to the power minus gamma into x minus y whole square divided by 2 sigma square. Now gamma and sigma, these are two parameters of the RBF kernel. You can tune it according to your necessity. I mean, for supervised learning algorithm, most people use some validation set and they tune lambda and sigma based on their validation performance. But understanding lambda and sigma is not really important to understand how RBF kernel takes us towards infinite dimension, which is this, right? So I will now prove how phi x dot phi y, that means the infinite dimensional dot product, is actually equivalent to a power of e. Let me now begin. So first of all, let's remove lambda and sigma for simplicity, and let's just keep x minus y whole square. So e to the power minus x minus y whole square. This can be easily broken down like this. And obviously, we can break down this like this because, I mean, you know that e to the power a into e to the power b equal to e to the power a plus b, right? That is why we can write this as simple multiplication as well, right? So multiplying in exponent is similar to addition in the exponent, right? Okay. Now this part is also not that important for us, so I will not really put a lot of attention on that. But this part is the most important, e to the power 2xy. Before expanding this term, I want you to remember this particular thing. E to the power x equal to 1 plus x by 1 factorial plus x square by 2 factorial plus dot 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 dot, and it goes up to x to the power infinity by infinity factorial. This is nothing but Maclaurin's series. I will repeat again, this is nothing but Maclaurin's series. You can look it up. That means, suppose x equal to 5. So e to the power 5 is equal to 1 plus 5 by 1 factorial plus 5 square by 2 factorial. And the more terms you add, the closer your value will be to the actual value of e to the power 5. Okay. So it's an infinite series. It's an infinite series. That is important. Now let's break this e to the power 2xy down. So again, just for simplicity, I am removing 2 because that is not really going to help me make my point further. So I am just taking e to the power xy. So it is nothing but 1 plus xy to the power 1 xy by 1 factorial according to this formula, plus x square y square by 2 factorial according to this formula, plus x cube y cube by 3 factorial according to this formula, and it will keep on going. And this is actually very similar to doing a dot product with this and this, right? I mean, obviously 1 factorial, 2 factorial, these things will not be there, that is true. And also 1 will not be there, but those are just constants. So we can actually, I mean, avoid worrying about them. That means doing this simple thing, doing this simple exponent in place of phi x dot phi y actually gives your model an idea that your samples have actually been transformed to a very high dimension, theoretically infinite, right? So there is very high separability. And RBF kernel of SVM, I have used it countless times. And many different algorithms that use kernel trick often use RBF kernel. It is very famous. So that is all for this tutorial. Hopefully there is nothing confusing about kernel trick now. The same concepts will apply to every algorithm that uses kernel trick. So thanks everyone. And if you like the video, don't forget to like and subscribe. Thanks.